Swayam Prabha. Digital India. Educated India.
Okay, so let's start the next lecture on integrated philosophy of mechanical and electrical domain thinking. Okay, this is like a mechatronics thinking. So far we have been discussing some part of it already, but like let us kind of like discuss it a little more in the with more examples and some kind of a formal thinking. Okay, so we will begin this lecture with it, with what is the idea basically. So as we have been talking about, if you recall, we have said that like in this philosophy you think in one domain to kind of ease out the things in the other domain. In other words, you need to think integrated in both the domains of mechatronic system, like mechanical domain and electronics domain. So typically the plant of the system would exist in the mechanical domain, and mechanical plant will have some complexities that are coming because of the natural phenomena. Okay, so for example, there is a friction phenomena which is natural to have for any of the motion systems. Then if you talk backlash phenomena, that will be there for transmission systems. Then like that, some kind of a non-linearities in the heat transport kind of a system, mass transport system. We have been so far looking at only like motion kind of a systems, mechanical, but you may have like systems which have other phenomena in the fluid domain. For example, you'll have a flow phenomena happening in the nonlinear kind of domain. So considering all these effects of different phenomena that are happening in the mechanical domain, how do we think that okay, we have to kind of ease out control of these phenomena in such a way that like your electronics domain also has some easy kind of a way to control. So you change something in the mechanical domain design to affect like something in the electronics domain. That is a central idea. Okay, likewise you can have in the electronics domain we do a control. Okay, so to ease out something in electronics domain, we have seen like we can do some modifications in the mechanical domain. Likewise, to ease out something in the mechanical domain, you do some kind of things in the electronics domain. For example, if you talk of this electronic fuel injection system, okay, so the previous systems, if you know of car engine, those who are working with Formula racing team, they might appreciate this a little better. The injection of the fuel into the system or engine was based on some kind of mechanical elements which are moving in some kind of a fashion. Okay, and that was some kind of a complex cam based mechanism to kind of open the the fuel whatever fuel port to kind of inject the fuel into the system at some particular time in the cycle of the engine operation of a automobile. Now this complexity of all these mechanical chains of like driving the cam and like affecting the fuel injection can be taken care of by using the electronics fuel injection system, where like by the digital command of some electronic interface, the fuel will be injected in the system. Now this kind of a way of doing things will have a more flexibility of planning the fuel injection into the engine based on many different kind of aspects of the working of the engine, and like make engine more efficient to work. Okay, so this is one of the kind of ways in which you can do something in electronics domain, to ease out the complexity of mechanisms that are to be used in the mechanical domain. Okay, so like that you'll find many kind of systems are getting developed nowadays, with the electronics kind of commands more than mechanical elements put together. So many machines can be operated instead of having these complex mechanical drives. You can have electronic kind of drives. One other example. Okay, you might have heard about these typewriters in the olden era, where they used to make they are very interesting mechanism used to be there for typing keys. Okay, so you press on the key on the keyboard, and the mechanism would kind of impact some letter on the paper. Okay, so that kind of a way of typing now can be eased out by you can see the nowadays what people are typing is based on all electronics kind of keys. Okay, so these are some of the kind of examples of other direction. Okay, which so far we have not looked at, and this has a value. Okay, so this has a great value in developing efficient systems which will work very nicely in conjunction with each other, and deliver the whatever is demanded or desired application. Hmm? Then this arm has been designed to optimize for the weight of it, if you see carefully. Okay, so weight, now one can kind of get a little bit more detail into what are the forces really coming on the arm. Okay, what are the forces that are coming on the arm when the arm is actuated by actuator? And imagine that you have this arm here. Okay, so we'll see that arm in a while, but you can just see, I'll just recall here there are these examples from the discussion on the CD-ROM drive and the scanner that we had already done in the class, that in CD-ROM you have a backlash free motion or friction free motion that is obtained by compliant mechanism in the mechanical domain, so that you can ease out control in the electronics domain. Okay, so that there are control challenges which are nonlinear control with friction, absolutely difficult to handle for especially for this nano positioning and reversal of direction with the nano positioning kind of a system. In focusing servo or in the tracking servo also, you may need to reverse the direction depending upon where the data is there on the surface of CD. And in scanner you can see that there are multiple reflectors were used to reduce the image size and reduce the cost of the photodetector sensor. Otherwise you need such a large kind of a strip of photodetector sensor, which is very expensive to produce in the first place. Okay, so that can be reduced the cost can be reduced by using these multiple photodetector reflectors. So these are the examples where you do something in the mechanical domain to ease out something in electronics domain. Okay, and many places you find that use of electronics itself will ease out a lot of designs parts in the mechanical domain for a lot of different examples. Okay, as we saw in the engine case, or say for example ATM machine. There also we'll find to ease out the drudgery of counting the nodes by a person. Okay, there are some mechanisms and some electronic systems that are used to count the nodes. Okay, so those are kind of examples we can think of. And again, I'm coming back to the hard disk drive. You have this arm, okay, for a hard disk drive actuator, and that has been designed to optimize for weight. Okay, so let's get into a little bit more of the thinking of why what. So what is the shape of this arm and why? It's basically to kind of like reduce the weight wherever the stresses are having like higher values. There only you need a material. Okay, where the stress values are very low or there is no stress, those parts of material can be removed. And if you imagine like when this arm moves very fast on the surface of the disc, what kind of forces are going to come on the arm? Think about that. Okay, if you think carefully, like this is a circular motion for the arm, and it is very fast motion, so one probably may not be able to uh, ignore the centrifugal acceleration forces. Okay, so the forces coming on the root of the arm, because this is a mass which is getting thrown, I mean or it has a tendency to throw out in the by the acceleration of omega square r. So any mass up here will have like omega square into the r kind of a force coming up there, and that force is basically in the outward direction, which is getting added up to the forces that are acting at the root here. Or at any section, if I kind of cut the arm, I'll see that okay, the mass which is beyond that cut will have a tendency to get thrown away because of the high speed. Let's say speed is omega for the arm. Then you can imagine that you'll have that force at, if you cut at different sections here, as you cut the lower and lower sections here at the root towards the center of the rotation of the arm, the forces or amount of material that is there beyond that cut will make it that the force coming on the on this cross sections are more and more towards the root. Okay, that is only we are talking about the centrifugal acceleration force. And then because of this tangential acceleration of the mass which is moving, we'll have some kind of a torque that is created here. Okay, so those kind of forces are going to come on the arm, and one can think about and make sure that the arm is sturdy. Arm should not kind of give away to these forces and first of all fail in the stress. But other more important aspect many times is this arm should not deflect more than what is required, or more than some kind of a tolerance that can be allowed. So because the arm deflection is what is going to cause a lot of errors in the system. Okay, so this deformation of arm should not happen so much. So many times we think that okay, stress is what is we have to design all the systems for. I mean, if you see your mechanical elements design course, many times we talk about stress more than anything else in the design of mechanical elements. Okay, so they should not fail basically. But more than that, many systems would have this requirement that instead of failing, they should not deform more to disturb the operation. Okay, that is more rigor or more stronger constraint that is put, which is which typically gives you a design which has much lesser stress than what is what will cause the system to fail. Okay, so keep in mind that when we design the mechanical systems, they are designed more for the stress, more for the deformation than for the stress. Okay, so we move forward and see this arm open up and see more details about it. Now this is more like an observation here. So you can observe that there is a coil up here, and when the coil current is passed, the arm will get actuated. Now one can imagine that very easily that okay, look, when the current is passed through this coil, okay, by the virtue of the placement of this coil, or the way the coil is designed, you see that this arm has a current in this direction when the other arm has current in the opposite direction. So if I look at this magnet, what should be the profile of the magnet in terms of its poles? Okay, so that see these are already these are opposite directions for the current. So if you imagine, if this magnet has the entire top as a north pole, then the magnetic field is going to be in only one direction for both the sides. And if that is the case, then the forces that are getting applied on these coils are going to be equal and opposite direction. Okay, considering that the field has a uniformity, and then your arm is not going to move at all. Okay, so the fact that the arm is designed to move means that on this magnet there should be on one side there should be north pole, and on the other side there should be the south pole, and that is possible. Okay. uh, so Another thing to observe is that we'll see this more in the detail, how one can observe the sea by looking at the magnet shape here. Okay, you can see only part of the shape, the rest part is below this arm. So if you see carefully the shape of the magnet, based on the shape one cannot kind of make out that okay where its poles are. Okay, so how do you observe the poles? Okay, that is the next question. So we'll see how to do that. And another thing that there is a direct drive to this arm. Okay, so this mechanical arm is not connected to some kind of a gear system here, or sector of the gear here, and it is driven by a motor or pinion which is attached to motor. That kind of a design is not there for the hard disk drive. No, we don't want to introduce any friction and any, I would say, any more friction. So there may be some friction at this joint. Okay, this is revolute joint, but it will have a bearing, and that bearing will cause only some kind of a rolling friction rather than any sliding friction. So we avoid the sliding friction by not attaching gear and a motor kind of a system, and motor system also will be bulky here. And then one can imagine, okay, oh, why not attach a motor itself here on this joint? It will be again the direct drive for the motor. You need a bulky motor. Okay, typically if you see the motor specifications, the kind of torques that are needed versus speed. So here the torque needed for getting this arm to move fast on the surface of the disc is relatively high, and because of that you will need a high torque kind of a motor which is going to be bulky. Typically motors are designed for small motors, will be having higher speeds and lesser torque, and that's where many times motor will always be used in conjunction with some kind of a gear transmission system. So in the CD-ROM drive we also saw the same thing. Okay, it was happening there. Okay, yeah, this is another kind of a thing that we talked about just now. So where are the poles on the magnet, and why they are at those places? So the reason for the poles, so one south pole will be here and one north pole will be here, because we want this coil to always see a field which is opposite to the field that this coil will be seeing, so that the total force on the coil which is produced by Lorentz force will be in one direction, will not be opposing each other. Okay, all right, then yeah, so next maybe when we discuss this more, I may have some gadget to show you how do you kind of see the poles of magnets. Okay, we'll try on some kind of magnets. I don't know whether we'll have this hard disk drive magnet itself available, but if at all that is available, I'll show you that only. So now you can see here little more kind of a details. Okay, so observe this carefully and think what observations you can make, and then if you have any questions that you can ask about. Okay, so think about some questions that you can ask. Okay, and then I'll propose these questions anyway, but you pause here for a while and think what kind of questions come to your mind when you see this kind of a design. Okay, so what you observe here is this very thin kind of a arm up here, and up here. There are three levels in which three layers in which you will have this arm put. okay, and actually the reading is only in this part. Okay, this is some kind of a read head here, the top side of the read head and the bottom side of the read head. Okay, so actually if you see this carefully, like this is some kind of a tweezer like thing which has to be opened up here, and the disc will be inserted there, and then the head will be going on both the sides. There will be one head on the top side and one head on the bottom side. So why this is kind of a design is there? Okay, and this arm, you see there is no head here at all. Okay, why that is so? So these kind of questions, you need to see and seek answers to these kind of questions. And then this is the actuator, hard disk actuator ka head. Okay, that arm ka head here. Okay, and this head is actually the reading, there is some kind of a magnetic sensors which are used to read the data on the surface of the disk. This is like a magnified form of it. So this 1 mm, you can see that small kind of a very small tiny kind of a mechanism is there, and there is this kind of a flexure mechanism, a compliant mechanism which is pressing the disk on the surface. This pressing the sensor, not disk, the sensor on the surface of the disk. Actually, if you see, then the obvious question comes in the mind that okay, since in this previous figure you see that okay, this is kind of once I remove the disk from within, they pinch each other, or they are in pre-stress kind of a condition. That means when I put it on the disk surface, this head is going to kind of press on the surface of the disk, and then that press, wouldn't it create any kind of friction on the surface? Why we want to kind of press this on the surface of the disk? Can you think about that? It may create a friction there, where we are creating this kind of additional friction. Isn't it counterintuitive that okay, we want to kind of have a magnetic reading happen with a absolutely no contact, so that we don't have friction disturbing the positioning of the head on the surface of the disk. Okay, so this arm will have this unnecessary friction that may be coming up. Think about this, and then it has something to do with the interesting way in which this system actually works. We move on now to the next kind of generalization of this concept of these different designs, such that they can be used now, or these ideas or different kind of concepts that so far we have been looking at these existing mechatronic systems, how they can be a little bit generalized for any kind of a motion control systems. So typical, so for mechatronics engineer, the motion control is a base thing to understand. I mean, we'll take this as a base example case of development of some of these ideas and concepts, but they can be extended and applied in the other domain of mechanical field. I mean, say thermal domain or manufacturing, or many other domains of mechanical phenomena that might be happening, for which you may have electronic control to be exercised. So we talk of motion control because this is one of the wider kind of use in the mechatronics domain. Okay, many mechatronic systems, you'll find that they'll have this some motion kind of a thing getting controlled. So let's say if you are asked to get a design of a single kind of a linear axis motion motion control system or mechatronic system that works at higher speed and has a 100 nanometer kind of resolution. Okay, so now we have a feel for what is 100 nanometer. You remember again we have talked about this in while discussing the CD-ROM. We have 1.1 6 micron kind of a spacing between the tracks of the CD, and we need like roughly this kind of a positioning accuracy. Okay, so suppose you are asked to design this. Now obviously based on CD-ROM drive you can say that, okay, look, for this kind of a thing I may go for compliant mechanisms, but are there any other kind of ways of doing the same thing? So say if you are given that, okay, oh, I want it over very short range. So if you see your CD-ROM typically maybe roughly like a short range kind of a mechanism when we talk of compliant mechanism. Maybe 1 mm, 2 mm kind of a motion, not even 2 mm, it may be almost like a 1 mm motion that may be happening in the CD-ROM kind of a head case for the compliant mechanism. Okay, so only that much motion I want, like no, I will go for compliant mechanism. If I want much smaller kind of a range, okay, still I can go for compliant mechanism, but there can be an option here of piezos. Okay, so piezos will have a very short range, and they may get you like the resolution better than 100 nanometer. Many times like piezo resolutions are much better than like they can be in the range of about 10 nanometer also possibility. Okay, so when you want very high resolution, but only over very short range, about 50 micron, 100 micron range, then piezos are preferred as a actuator mechanism. And now we are talking in general of like bigger size system. So in some CD-ROM drive systems also, people might have in the past tried out. I mean, I've never seen in piezo used in CD-ROM drive. There is a reason for that, but like people might have tried that in the beginning to kind of like see the motion possibilities with piezo to kind of give you that much accuracy. And one of the bigger disadvantage of piezos is that like see, one good advantage is that they can be positioned better than 100 nanometer. And why that is happening, if you see carefully, piezos typically require very high voltage when they have to be actuated. Okay, so the voltages are easily in the range of 50 100 volts kind of range, and that much voltage given, and it deforms very small in even at that voltage. Okay, based on their like the different kind of a coefficient like D33 and those kind of piezo coefficients. So if that small kind of a deformation is there with a very high voltage, one can see that if I apply millivolts, I'm going to get like the deformation to be much lesser in say some few nanometers kind of accuracy. So that from that perspective, the piezos can be given very robustly, like very small kind of motions very easily. So it's just a little bit of a common sense thinking one can do and say that, okay, oh look, the resolution of the voltage that I can apply is maybe about 1 volt 2 volt kind of resolution I can apply, or like in the even millivolts is fair to kind of apply. The noises are like maybe in the same millivolts kind of a range, but I can go beyond 10-20 millivolts. I will not find like the noise will be bothering you so much. So piezos would be very good kind of actuators for very small kind of a resolution, and of course you need to pay more for the cost of the driving piezos. Like you need to have a driver which is giving you these high voltages for the piezos to drive, and they should not have very large range demand. Okay, so if the actuator demands like, okay, I want to move over larger distances, then piezos may not be a good choice. Nowadays also, like you'll find there are something called inch form motors. So let me see if I can give you some kind of a flavor of that in so these inch form motors, maybe we'll give when we talk about actuators. Maybe we can talk a little more about. But basically, these are like multiple piezo actuators together working in tandem. in the sense that they'll push something like in the form of a wave. um, so maybe the closest example I can give here is something like a centipede. Have you observed how centipede moves? That motion of the centipede with like so many legs moving in tandem creates some kind of a small wave. As you see that the centipede moving, you see some waves are going because of the leg motions, and those waves are actually like if you imagine those are pizzos. Okay, so the way that pizzos are like moved, like the motion takes place in that kind of a fashion, and then one can kind of enhance the range of piezo actuators. Okay, and there are actuators people have designed like that, by using this kind of a inch worm motors. That's what they call it, based on the worm kind of a motion. The similar principle is used, biomimicking of the similar principle is used. So those are used for enhancing the range with pizzos. Okay, for moderate range, like the 1 mm, you can go for compliant mechanism designs. Large range, you can have or rack and pinion, or your screw drive kind of designs. And extremely large range motion, you can go for the belt drive systems. Okay, so like that there are like possibilities for different kind of a motion control systems. And so one can say, okay, look, I go for like large range. uh, if I go for large range belt drive or the some kind of a system, and will I get 100 nanometer resolution? Oh, no, that is not possible to get, right? So you cannot just do this. Okay, so large range, we have seen also possibility of large range in the CD-ROM drive. Okay, so CD surface, you have to move larger distances by 100 nanometer resolution. Only like the short range of up to 1000 micron or 1 mm was taken care of by the compliant mechanism, but rest of the motion was coming actually by the rack and pinion kind of a drive. So you use some combination of rack and pinion, belt drive or screw drive along with compliant mechanism. Okay, so there will be two actuators here in this kind of a case. If you want to go really 200 mm like a large motion, and with the resolution of this 100 nanometers, then you need to have a double actuator system. So two actuators are there, but only one sensor will be there. One sensor will be looking at very high precision like the motion that is happening, and then it will give a feedback to both of these systems in an interesting kind of a way. How to design control for that is itself is an interesting control algorithm design problem or development problem. So that problem will be solved in the mathematical domain to implement control algorithm which can take care of moving the both the actuators in some kind of a coordination with each other, such that you get this motion over the larger range also and larger resolution also. So together that can be achieved. So each of these things one can again kind of categorize as, okay, what is a plant here, what are the sensors and actuators for different cases and things, and why they are used. Okay? This is another kind of a thought process one can get into and be able to kind of appreciate, okay, what people have like done in the design in this case. So based on that kind of a thinking, one can come up with this filling up this chart of the range versus resolution chart, and what are the actuator systems that you can see, or say, what are the control systems or actuator sensor together which can put in these bubbles here. Okay, so so typically if you see like range which is higher and resolution which is lower, okay, this domain is little difficult to obtain by a single actuator. Okay, so here we need two actuator kind of a design. Okay, but many other places, like if you go linearly along this direction on this diagram, then you find that, okay, oh, these are like it can be done with a single actuator, single sensor kind of designs. Okay, So also, like typically people may not be interested in this where the range is very low, which is coming almost like a resolution itself. That kind of a thing, I mean, will not have a requirement where the range is so low that it comes almost close to the resolution requirements, which is impossible for. So this is like unfeasible or empty area. You'll find no bubbles would be required up here. Mainly, like the systems will be centered around these. Most of the systems will be centered around these, and some special systems will require very high resolution and high range. Typically, combination of high resolution and high range will be very small number of applications. Okay, so in the nature also, if you see like something which is happening at a larger range, there'll be hardly the resolution of those things will be low. Okay, if you see the systems they developed also mechanical systems developed, for example, the crane system, okay, that transports material from one place to other place for the building construction or some other kind of application. There also you see that the positioning resolution or resolution of the placement of the object will be much lesser, much coarser than for smaller system like say some CD-ROM drive system, or that is extremely small, but you can kind of see through that wherever there is a high resolution requirement, typically the ranges are going to be small, and wherever there is a larger ranges, the resolution also will be a little coarse there. Resolution requirement also will be little coarse. So will typically will move along the some kind of a one axis up here, central axis here. Okay, and there are some special systems only they'll be having this kind of a requirement of both together. And this is interesting area. I mean, like nowadays with the advances in the nanotechnology and microtechnology, this area is getting now more and more kind of explored for interesting research applications there. Okay, so we move on to the next slide. So you pause here and think how we can fill in each bubble, and you have your own kind of a filling done here on the paper. Okay, this kind of a thought process will be very interesting to open up some of the concepts in your mind. Okay, even if you go to wrong, don't worry about. Okay, let it be whatever you think, whatever comes to your mind. That will raise some kind of a questions later, and then when they are kind of clarified, you'll have some form conceptual understanding that will be happening here. Okay,